Hello, my name is Zachary Shalson, and today I'm going to be presenting to you all about color mixing. So in order to start getting into color and what color mixing actually is, the very first thing we need to talk about is what is light and what exactly is color, because we see it everywhere around us, but what actually is it? So going first into what is light. Light, at its most basic form, is a wave. So you can kind of think of a wave as something that you see in the ocean or something that just travels around everywhere, but really, really tiny, so really difficult to see. Now, some waves travel with big wavelengths and some travel with really small wavelengths. And right in the middle of a sweet spot of these big and small wavelengths, we have what's called the visible spectrum. Now, this visible spectrum is where we see all the colors that we can see in the world all around us. And if the light has a much shorter wavelength, it actually looks blue. So if you see any blue light anywhere, like my shirt, for example, that is reflecting a very, very short wavelength of light. However, if we have these really long wavelengths, they actually produce red light. So if you see anything red, I don't have anything red with me right now, but if you see anything red in the world around you, that reflects a really, really long wavelength. However, we can get even shorter wavelengths than blue, so these really short wavelengths, we can get them even shorter. And for those are going to be more of your UV, your ultraviolet rays, your X-rays. So if you go to a doctor and you see your bones, those are using X-rays, which is shorter than blue light, and gamma rays as well. But if you were to go even further longer than your red light, you would go into your infrared, but you can go into your microwave, so the things you heat up your food with, or you can go to the radio waves, what you listen to music with in the car. Now, I'm going to talk about this thing called the electromagnetic spectrum. This is just a diagram showing all those different wavelengths, the big waves and the really, really tiny waves. So if you direct your attention to this chart right here, way over here we have these super long wavelengths. These are going to be your radio waves, so once again the music in the car, your microwaves, your things to heat up your food, your infrared rays. These kind of track more heat signatures, so any kind of like night vision goggles, these are using kind of infrared waves. On the flip side of that, we have our shorter wavelengths. We have your ultraviolet, your X-ray, so if you go to a doctor, the bones, and your gamma rays over here as well. But right between them, we have this beautiful sweet spot that we call the visible spectrum, or visible light. And this is where you get all your colors of the rainbow, your red, orange, yellow, green, blue, purple, your violet. This is where you're going to get all those colors that you see in the world around you. Now, when you think of colors, you might think of your most basic primary colors. And when I was younger, I learned that the primary colors are yellow, red, and blue. Now, you might see this everywhere. You see red, yellow, and blue pretty much in everything around the world. This is what they use in printers for ink. So anytime that you combine colors in the printer, you're combining your red, green, or your red, blue, and yellow pigments. Now, from these primary colors, what happens when you mix them? You get new colors. So if you mix yellow and red, you're going to get orange. If you mix your yellow and your blue, you're going to get green. And if you mix your red and your blue, you're going to get purple. Now, these are your secondary colors. You can go even further beyond this to your tertiary colors, which is your citron, russet, and buff, which is essentially just your yellowish gray, purplish gray, and your bluish gray. And if you can go even further to your quaternary colors as well. So if you look at this chart right here, this kind of depicts how those colors mix. So you start with your primary ones, your basic yellow, red, and green, or your yellow, red, and blue. Then you move to your orange, green, and purple. And then you start getting into your more grayish colors down here. But we're not super interested in those grayish colors, because when you mix more and more colors together, it gets darker. So if you have a lot of paint just lying around and you start mixing them all up together, it starts to turn into this brownish, blackish sludge that you wouldn't really want to use in any kind of paint. So this is something called subtractive color mixing. And we're going to talk about the opposite of that in just a minute. But subtractive color mixing is when you're using your pigments, when you're using ink, paint, crayons, pencils, anything that kind of you're seeing in the world that's not really light-based is all subtractive color mixing. So if you look at the diagram right here, we're going to take a big light bulb right here, that's going to shine white light. Now what happens when the white light comes in contact with a piece of paper that's purple, what actually is going on, or it reflects blue and red light, so you are in fact only able to see purple, but it's actually absorbing every other color except for red and blue. And that's how you get subtractive color mixing. So you start out with this big white bright light, and then as you add more colors to it, it becomes darker and darker and darker. And the opposite of this is actually additive color mixing. So additive color mixing is when you're using mixing of colors based on light. So this is like your flashlights. So if you have flashlights or even LED strips lying around, this is where those come to be important. So the complete opposite of subtractive color mixing, when you start off with white light and end with this darkness, is when you start at darkness and you end with white light as you add more colors to it. So you can kind of think as white light as adding up every other color together, and that will produce one single beam of white light. Now just to get into a little bit of history, I know that history can be a little tough, but a little bit of the additive color history is that systems of additive color were motivated by this guy named Young-Helmholtz theory of trichromatic color vision. Now what this actually is we have this beautiful image of an eye, or a beautiful diagram. And it basically collects the light at the front here, and as you get further back into your eye, you see all these different rods right here, and you notice that all these rods are red, green, and blue. Now this is actually where we're going to start to change our primary colors from your yellow, red, and blue to red, green, and blue. Now this was just a theory at this point that we had these different color rods receptors in our eyes. But it wasn't until James Clerk Maxwell, who's considered the father of additive color, actually helped to prove this theory with a really fun experiment. What he did in this experiment was he took a ribbon, a beautiful ribbon, and took 3 different images of it. But for each image, he added a different filter. So for the first image, as you see up here on the top left panel, he added a red filter over the camera lens and took one photo of the ribbon. If you move to the right panel, you see that he added a green filter in. And then down here you see he added a blue filter in. So he took 3 different images with 3 different filters. And then what he did was he put each image one on top of the other. And what he saw was at the end, you were able to see every color that the ribbon actually had on it. And that's kind of how he proved this theory that our eyes have these color receptors that are red, green, and blue. Now, we could do this experiment with any kind of image. So down here we have an image of a house. It may not look like a house at first, but we have the image of the house with a red filter on, with a green filter on, and then with a blue filter on. And then what happens when you combine all 3 of those images together is you get this beautiful, beautiful image of this house with this beautiful picture of the mountains in the back, and you get the sky as well. Now, even though each image separately looks kind of wonky, doesn't really look all together, you have to add them on top of each other, and that's why it's called additive color mixing, because you're adding the colors together. So like I said before, we're transitioning away from the red, yellow, and blue color wheel to now a color wheel that's red, green, and blue. Now, we're going to actually test some of these theories to combine them, but what happens when you combine red and green light is you actually get yellow light, which is really weird to think about, because you usually think when you add blue and yellow, you get green. But now you're adding red and green to get yellow. Now you can also add red and blue together, and that'll give you a magenta color, so that's your purple color. Or you can add blue and green together, and that'll be your cyan color, or your turquoise. Now, what happens when you combine red, green, and blue is you actually get pure white light. We can actually go ahead and test this as well right over here. So as you see right here, we have a beautiful strip of LEDs. And I have this fun little sensor right here that actually allows me to change the color of what these LEDs are going to show you. So if I hold my hand over one of the sensors, we're going to see red light coming from the LEDs. If I hold my hand over the middle sensor, we see a line of blue light. If I hold my hand over this far left sensor, we get green light. So we're going to test a few of these different color mixing ideas right now. So we're going to combine red and green light. Take a second to think. I just talked about it, but red and green light is going to produce yellow light, which is honestly a little bit weird, a little bit hard to wrap your head around, but red and green do make yellow. Now, we can add blue and red, and this will give us our magenta or the purple color. Or we can add blue and green, and this will give us our cyan color. Now, what happens when we add all three? We're going to get pure white light, which is super, super awesome. And this just goes to show how we get color mixing as additive. Now, what's also fun with this is I could do fun things like this, where you can kind of see all the different colors of the rainbow as I move my hand all throughout the sensors. Could combine a few times, and yeah, just having a lot of fun with these sensors, playing around with those colors. Now, you can actually test this for yourself too. So on all computer monitors nowadays, or TVs, there's these little tiny things called LEDs, which is essentially combining red, green, and blue light to produce every other color that you see on your computer. But the thing is, these LEDs are very, very tiny. So if you're just looking at your computer, you probably won't be able to see it very well. You have to get a little magnifying glass, hold it right up to the screen, and that way you can actually see the individual LEDs. Now, a cool little test just to prove all this additive color theory to yourself, you can go ahead and look at a picture of yellow. And as we just saw before, yellow is made up of red and green light. So if you have your little magnifying glass, go ahead and hold it up to the computer screen really, really close, and you might be able to see the individual red and green diodes, or the red and green LEDs, but notice how you won't be able to see any blue. And that's because when we're talking about yellow, you're only actually able to see red and green with the absence of blue. And with that, thank you for listening to my presentation all about color mixing.